If you want to predict the direction of a dipole for a molecule, you've got to be able to draw the Lewis structure. You've got to be able to analyze formal charge. You've got to be able to analyze how there might be resonance that moves the formal charges around. You've got to be able to look at electronegativity differences. And you have to be able to analyze geometry so you can see where the atoms are three-dimensionally in space. And then you can piece together where all the charges are on the molecule three-dimensionally in space to see if there's one side of the molecule that has more positive and the opposite end with more negative, which would be the direction of the dipole. So all of these pieces have to come together just right for you to be able to properly identify the direction of a dipole on a molecule. So let's look at an example. Let's see. Let's say you've got so let's say this is your formula that's given. You have to start by drawing a Lewis structure. So you would put your carbon in the center, bonded to the oxygens, and you would put the hydrogen in last because it can only have one bond, and generally you want to put as many bonds on the central atom as possible because that atom is less electronegative. The carbon is less electronegative than oxygen. It's more willing to share, so it's happy to be in a position where we've got it sharing multiple electron pairs. And then we've got to count up the valence electrons, so 1 for hydrogen, 4 for carbon, 6 on each oxygen, and then 1 from the negative charge, because that means we have 1 more electron than we would normally have for everything to be neutral. So if we add all that up, we get 18. So far I've used 6 to make my 3 bonds, so I've got 12 left. And so I want to start by putting those 12 electrons on the oxygens, since they're more electronegative and they attract electrons more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's it. I can't put any more in. Is the molecule okay? No? What's wrong with it? Right. The carbon does not have 8 valence electrons. It needs to make its octet. So it needs more electrons. Can I just put another pair on it? No, I've already used all the electrons I have. If I put more electrons in, it's not going to match this formula anymore. This formula is communicating a certain number of valence electrons. If I put more in, if I put 2 more in on the carbon, that would be HCO2 3-, because that would mean I put 2 extra electrons in. So I can't just do that. It's not the same formula anymore. So I've got to share some of the electrons I already have. Does it matter which oxygen I do that with? No. But when I see that I can share from multiple locations, that's a big clue that there's resonance. So I need to recognize that here, and that these electrons are not going to be stationary. They're going to be moving around in these orbitals over multiple atoms. So initially I could think about moving one of these pairs in here and just maybe redraw what that would look like. And then I need to analyze the geometry and look for formal charge. So is there any formal charge here? The way to know for sure is to calculate it for every atom using that formula, right? So the formal charge formula is the normal number of electrons that it would need to be neutral from the periodic table minus the lone pair electrons and half the shared electrons. So for the carbon and the hydrogen, it's going to be 1 minus 1 for the hydrogen, 4 minus 4 for the carbon. Those are both no formal charge. The oxygen I've drawn with the double bond is going to be 6 minus 6, so that doesn't have a formal charge. Does anyone want to see those worked out? What? So let's look at the oxygen with the double bond. So the oxygen with the double bond, oxygen is in group 6A, so it should normally have 6 valence electrons. It has 1, 2, 3, 4 valence electrons in lone pairs, and it has 2, 4 bonded electrons, so that's 6 minus 6. So that oxygen is neutral. Is it possible for all of my atoms to have no formal charge here? There's plenty of molecules where all the atoms don't have any formal charge, and that's because it's generally stable. More stable if there is no formal charge. So if you drew a structure that had a whole bunch of formal charge all over the place, you should think about redrawing your skeleton, because it's probably not very stable, right? The best structure will have complete octets or noble gas configurations for the atoms and a minimal amount of formal charge. However, I know if there's an overall charge on the molecule, then there has to be a formal charge somewhere that adds up to that overall charge of -1. So if my molecule's formal charges don't add up to the overall charge, I either put the wrong number of electrons in or I'm not calculating formal charge correctly. So in this case, if we look at the other oxygen, the bottom oxygen, it has to have a -1. So let's make sure it does. So oxygen is in 6A, so it'll be 6 minus. This one has 6 lone pair electrons and only 2 shared. So that's 6 plus half of 2 or 1. That's 6 minus 7. And that gives me a -1. So here is where my formal charge is. Is it correct to say that in this molecule, the bottom oxygen will be negative and the top oxygen will be neutral? Well, I just calculated those formal charges. Why is that not correct? Resonance, right. So I have to also recognize, since I know that there's resonance, I know that either of those oxygens could have pushed electrons in to make a double bond on either side. So I have to realize that this structure, it doesn't just look like that. It could have easily also looked like this, which would have made the other oxygen the one with my negative formal charge. So what does the real structure look like? It's the hybrid of those, or the average of them. And so if I have one negative formal charge on the whole molecule, but it's spread out over 2 atoms, each one has half of a negative. Or maybe if this molecule weren't so symmetrical, if I had a negative spread out over 2 atoms that weren't sharing them evenly, it would at least, I would show that it's a partial negative on each oxygen, right? But if I want here, I can show that the real structure is going to have those electrons in resonance and a partial negative or half of a negative on each oxygen. And so I'm starting to recognize something about polarity, because I'm seeing that the 2 oxygens are centers where I have more negative charge than I have on other areas of the molecule. And that's what polarity is all about, is showing which areas are negative and which areas are positive of the molecule. To do a complete analysis of polarity, though, first I have to be able to draw the molecule with the correct geometry. So what's the geometry here? I only have one central atom. My oxygens and my hydrogen are only attached to one atom. That's the carbon. So I don't need to label their geometries. But I would need to label the geometry for any atom that's attached to at least 2 other atoms or more. So in this case, that's only the carbon. What's the geometry of the carbon? Trigonal planar, right. It's got 3 atoms attached to it, so it's trigonal. Any atom that has exactly 3 other atoms attached to it is going to be trigonal. The question is it trigonal planar or is it trigonal pyramidal? And the difference is whether or not there's a lone pair on the central atom or not. So when there's no lone pair, the 3 atoms attached to it, the 2 oxygens and the hydrogen, spread out evenly. If there were a lone pair on the carbon, that lone pair would take up space. That would be an area of negative charge, and it would be pushing the oxygens and hydrogens into the base of a pyramid. So here it's trigonal planar, so I want to redraw that, representing as best I can the correct angles that are going to be here. And so I know that in a trigonal planar, the 3 things are going to spread out as much as possible, and the angles will be about 120. Right? So if it's flat, in a circle I've got 360 degrees. If I've got to divide that by 3 things, I get 120 for each of those 3. So now I've got my 2 oxygens and my hydrogen. So when I display the molecule with the correct geometry, and I also recognize, due to this resonance, I have some charges already. I'm almost able now to look at the polarity. One other thing I have to do before I can analyze the overall polarity on the molecule, and that is, right, you've got to look at the electronegativity differences on the atom. So that would have to be given 2.1, 2.5, 3.5. So those are the electronegativity values. So anytime an atom's more electronegative, it's going to attract electrons it's sharing with other atoms. So carbon's a little bit more electronegative than hydrogen, and oxygen's more electronegative than carbon. So those electronegativity differences will also create some partial charges. So I need to think about where they are spatially, as well as where the formal charge is spatially. I've already determined the formal charge spatially is spread out over 2 oxygens. The partial charge will have a little bit of partial positive on this hydrogen because the carbon's pulling some of the negatively charged electrons away from it. Right? If the electrons between the carbon and the hydrogen were shared evenly, then I wouldn't have any partial charges as a result of that bond, because the electrons would be spending equal time on both atoms, and that's what they need to be neutral. But if they're shifted toward the more electronegative atom, it's going to have a little bit more negative charge due to the presence of those negatively charged electrons around it. So that's going to create, so looking at that bond, the electron shifting from the hydrogen to the carbon, what kind of partial charge will be on the carbon? It would be a partial negative, right? Because if the carbon's pulling electrons away from the hydrogen, is the carbon going to have an overall partial negative on it? Probably not, because since the carbon-oxygen bond is more polar, there's a bigger electronegativity difference between carbon and oxygen than there is between carbon and hydrogen. We want to focus the most attention on the electronegativity differences that are the greatest. So if the carbon has the greatest electronegativity difference with oxygen, that's the biggest difference we have in the molecule, that's the one that's going to affect the partial charges the most. So we can put a partial negative and a partial positive due to the electronegativity differences that are larger there. So now I've got my molecule with the right shape. 3-dimensionally, this one happens to be flat, so it's a little easier to draw, but 3-dimensionally shown with the atoms in the right 3-dimensional spatial arrangement, and I've got all the charges in the right spatial locations. So now I could think about whether or not there's more negative on one end and more positive on the other end, or whether things are symmetrically distributing the positive and negative charges. So clearly, there's more negative. Obviously, the negative's on the oxygen. The positive is on the carbon and the hydrogen. So I have an arrow that should go from the center of the positive charge, which is pretty much between the two partial positives, and that will go to the center of the negative, which is between the two oxygens. So because of the resonance, both oxygens carry the same amount of negative, so the center of negative charge is between them. So you could draw your arrow there, or as long as it wasn't too cluttered, you could draw your arrow right over top of the molecule if you wanted.